Y'all are doing liquid nitrogen, right? For Earth Day? Okay, sweet. I got the tank coming from Grants Pass at least. So it's like a bigger dewar. I'm not sure how many liters it is. And then we'll just have to figure out if you wanted to like practice on Thursday. Or like how many times you want to practice, because you have this Thursday, next Thursday, and then Friday. So if you just wanted to practice next Thursday too with the ice cream, that might make more sense. But just let me know so we can let Nicole know, and she can get supplies for you. Cool.
So for these, to do the calculated pH, so I was doing it just like we did in the homework problems, but my pH numbers are not quite adding up to what even the measured pH was. So I don't know if I've missed something completely.
So it looks mainly okay. I'm just wondering, because is this moles or molarity? Maybe something that's slightly off there. Because you should find like initial moles, right? So I don't know if that's like millimoles. Is that millimoles?
Yeah.
Okay, that might be fine then. So I don't see anything. I feel like you're off by an order of magnitude, but the math looks correct. But I have to maybe plug it into a calculator. But that's like the right idea. Is you're just
okay.
Let's see. So I'm bad at mental math. So if we do that, divided by, which is what you got. Oh, seems okay then.
So I was just kind of cruising along, and what really got me was, let's see here, I think it's, so this one, that should be almost the equivalence point, right? Because we were almost at like 7 pH.
Yeah.
But my calculated pH is still coming out as 2.1.
Something seems off. So 13?
Yeah. So 13 is this one, which we got a measured pH of 6.65.
Yeah. Here, so let's start from the beginning. So we had 10 moles of E. So we had that many moles of acid initially. That's not what I wanted to do. Minus, but then at this point we should have, so 0.01 times so you should have a negative number at that point because that you're past the equivalence point. So then you have like, so then it should be like that much excess of POH.
Right, that's what I was thinking, like at some point I should have been reaching the negative.
Yeah, so it, like mathematically, it probably should have been around here.
Okay.
If you measured everything like precisely and everything is perfect.
Yeah.
Because at least mathematically, once you get to 10, that would match the same.
Right.
So then that should be your equivalence point. So I'm not sure.
I'm not
I
sure
still
where
think
I've gone
something
wrong.
might be a little funny. I
Okay.
still think that might be funny, because I get 1 times 10 to the negative 4th moles, but then that would be 0.1 millimoles for starting.
Okay. Okay. I'll go back and just double check, but,
Yeah, so
I
I think
wanted
that might
to-
be 0.1.
okay.
Yeah, because that one, I thought I remember calculating it myself and it being like 3,
Okay.
but it's like your method's right, but yeah, I think maybe that might be a little off or something.
Okay. Okay. Perfect. Thank you.
Oh, Oh, I didn't check them this morning.
That was pretty sweet. I meant to send you a picture also on Friday, because like, the top little piece of that, the tube was yellow, and then there was one little ball stuck at the bottom, and everything underneath it was purple.
Oh, that's funny.
And there was like a little bubble of oxygen.
Yeah.
There with it. It was really, Brandon's got a picture of it, I just didn't have it.
Oh,
on me,
nice.
Like when we saw it.
Is having a little bit of a hard time on the math on the titration lab. Are you available after class today?
Yeah, ask me after class. All right, let's go ahead. What happened to your class today? All right, well, inform your class of what they missed, because we're going to mention Earth Day projects again, so that was a good transition on the algae subject. So if you want to make that your Earth Day project, just let me know what materials you need. So that's going to be the focus of our lab this week and next week. So lab Thursday. So please let me know, especially this week, let me know this week what materials you might need, unless you're supplying them yourselves or bringing them from home. But if not, just let me know ASAP so you can have things on Thursday to play with and kind of plan what you're going to do. So same thing with the poster board. Don't forget poster board on Thursday, unless, again, you need me to supply it, and just let me know after class or something so that I know what either myself or Nicole needs to purchase us for Thursday. And then I've talked to y'all about liquid nitrogen, so that's a go. And somebody else emailed me lab materials, but I haven't heard from other people, so I don't know if that means you're just buying your stuff on your own or what you're planning, but start thinking of stuff. And I do have a few like pre-canned things. So I mentioned like the silicon bouncy ball, red cabbage is always a good standard. But if you need materials, if you want to do those, just let me know so I know to bring some cabbage and whatnot on Thursday. Are there any questions about this so far? And if somebody mentioned composting too as a possible topic, and you can get creative on how to make it interactive. You could even have just on your poster board little flip-up visuals if you wanted to ask like questions from people, especially if you have a topic like composting that's maybe harder to show, how something decomposes over time, but instead you can have some trivia maybe to get some interactive approach. And then, of course, just a reminder that extra credit for doing Earth Day. So Earth Day is going to be from 11 a.m. to 2 p.m. But if you can stop by just, any amount of time, I don't expect you to be there the whole time, but at least part of the time. And if you can't be there the full time, if you could just leave your poster for people to at least walk by and admire it, that would be awesome. And so the other big thing that we should talk about is a field trip. So that's been in the works in the background. And so it looks like we're clear for the date of May 11th. And so that does work out well for y'all. So we're going to be combined with the Grants Pass 223 class, but I thought y'all were small. They only have 4 students. So. Yeah, so we're, I guess, large comparatively. But so that means we'll be combining with Grants Pass. What they do is they can accommodate 60 of us a day, but then groups of 15. And we don't have the exact time from them yet, so I'm still waiting. So I'll have people sign up for like an earlier group, a second group as they get back to me on the time. So just keep that on your calendar. Again, we probably won't have lecture that day, so you can have, obviously, the commute time. So I'll just add there 2 groups, same day. And so we do have to fill out paperwork for that. So up at the front is the 2 things you need to do to sign your life away. So one is just some emergency information, and the other just general purpose waiver, blah, blah, blah. And then if you can't make the field trip, we will have alternate assignments, although I really hope y'all can make it. It should be lots of fun, and there's like hiking afterwards that we could do. So I really hope y'all can come, but there will be alternative assignments available. And so those will probably be like watching some video or doing a report. So just keep that in mind. Again, if you can't make it, there will be an alternative assignment, but I really hope to see y'all there. And so, of course, make sure you sign those field trip permission slips ASAP so we can have them for our records. And I don't know how to spell slips. And if you're under 18, I think you need a parent signature. I think that applies to 1 or 2 people in here maybe. All right. Questions about?
Okay, so I go in camps like a lot, and White knows and
Yeah.
you can boil your clothing.
Actually, they said not to wear any clothing that has ever been in a cave. So they don't even trust that you can adequately.
They
Uh,
have for your boots there, I went last summer, they have hydrogen peroxide ones. So they give you a button if you can decontaminate your boots there.
Nice. Yeah, they told me like no clothing that has ever been in a cave ever because of the white nose bat fungus. So, but I'll send out more details about that. We just have to get the form signed ASAP. And then homework's also at the front, so you can grab that. Other questions, comments? All right, let's dive into KSP then. All right, so now we're kind of answering, and I feel like we're finally going back to first quarter stuff. So do you remember vaguely like those solubility rules, and then some of them were vague, and then you would like read two sets of rules, and it would tell you like, oh, calcium hydroxide is soluble, oh, calcium hydroxide is not soluble. And you're just left with this, well, I don't know, why is this so confusing? Why don't we have a clear answer? And now we're kind of going back to that and looking precisely then how to calculate our solubility. And so now, going into KSP, well, we learned, at least from first quarter, so all ionic compounds dissolve in water to some degree. And of course, we saw that many compounds have low solubility, that they're essentially classified as insoluble. Does anyone remember any of those classic examples? Insoluble compounds. Yeah, so silver iodide's like a good one. Well, at least or silver compounds. I don't have a solubility chart. So yeah, we can put silver iodide. And so, right, we saw these compounds, and we saw them a lot with our double displacement precipitation reactions, where we put two solutions together, something would fall out, and so we classified that as insoluble. But now we're going to kind of go back and really look at what it means to be insoluble, to what degree it's insoluble. And then we're going to see how, of course, these concepts of equilibrium that we've been talking about can be applied to salts, how to dissolve them, how to use our equilibrium constant, and also how we can use our solubility properties to purify compounds and separate out different mixtures. And so first we have to define KSP here. And I feel like the general expression looks really confusing, but then once you break it down into what it's saying, it's pretty simple. And so let's look at the example as we both look at this generic form. And so you kind of have, right, you're starting with your ionic solid, but let's do our example as we do it. And so we're looking at the dissociation of lead chloride. So just start off with our solid lead chloride. And then, so notice, so it does this, we still have our double-headed arrow for equilibrium. So now we're saying, right, a small portion of it is actually dissolved in solution. We're trying to quantify that exactly. And now notice these, our little subscripts become our coefficients. So all that is saying is how many equivalents, right, of each one of these we produce in solution. And so we're looking at our formula. Well, it disassociates to make lead, and we just have one equivalent of lead. And then, of course, we have the charge on there. That's all that is. And N is just one in this case, right? One equivalent of lead. And then how many equivalents of chloride do we make? So 2, again, just from our formula, so 2, and that's all that little m was, so our subscript, so 2 chloride, and then obviously we just put the charge on it, and now we can formally put aqueous here. And so now it gives us this expression here, and let's go back though and derive it. So what the heck is KSP? Well, now we're just writing what it would be. And so KSP then is just equal to the product of your ions. And so that's all that's shown there. Except, so now we take, right, lead to the power of lead. So in this case, right, it's just 1, because we just made 1, times our concentration of chloride. So we have our concentration of chloride, and then notice we have to square it, right, since we have a 2 there. And so that just gives us our KSP expression. And so again, concentration of lead then times our concentration of chloride, and then squared to account for the 2 equivalents there. And so this is just a table of KSP constants. And so you can, of course, just get a sense of kind of what's more soluble than others. And so obviously if it has a teeny tiny number, it's very insoluble. So lead sulfide, for example, is 10 to the negative 29, while like calcium sulfate is 10 to the negative 5th. So that one could be more ambiguous when we just discuss our general solubility rules. And some people may say calcium sulfate is slightly soluble, and now you can see that's why, because compared to the rest of these, it is at least slightly soluble. And so the thing that you're going to want to calculate is our molar solubility, so S. And so solubility is just the amount of solute that will dissolve in a given amount of solution at a particular temperature. And then, so then you have this molar solubility is the number of moles then of solute that will dissolve in a liter of solution. And so for this general expression, so for our dissociation reaction, this is your molar solubility, but let's derive this, and then we'll see how this formula works out, because I think the formula is more confusing. So let's say we want to calculate the molar solubility of lead chloride, except we're not going to look at this formula, we're just going to go through the ICE method, and then we'll find that it gives us this formula, but ICE is kind of, I think, easier to understand. So doing our ICE method, we just start with our reaction. So we're just writing down the dissociation. So starting with our lead chloride, then we're going to make lead 2+ in solution and 2 equivalents of chloride. And so if we want to calculate molar solubility, now I'm going to substitute in S. So now this is our initial S, and so then plus S plus 2S. So now just plugging in how much it would make. So again, we would make 1 equivalence for lead, 2 equivalents of whatever S is for chloride. And so now we can plug that into our KSP expression. So remember, we said KSP was just our lead concentration times our chloride concentration squared. So now we can plug in these values of S. So equals S times 2S squared. So now we can do some math and solve. And so now we get 4S to the third equals our KSP. And so now we just have to solve at this point And so let's pull our value. So lead chloride was 1.17 times 10 to the negative fifth. Is equal to 4s cubed. And so now you can do algebra and solve. So divided by 4. And then we need to take the cube root. And so let's pause there for a second and go back to our formula. What did it say the formula was? So it said molar solubility was N plus M root, and then KSP divided by N to the M times M to the N. And well, if we plug that in to our lead chloride scenario, so now I'm just going to rewrite the molar solubility formula here. So we had just said that our molar solubility, so S was equal to M to the N root KSP over N to the M, M to the M. And well, let's translate that. So our N, what was our value of N? So 1, and then what was M? So 2 to the 2. So that looks like we just derived. So KSP over 4 then. And then N plus M, so you said N was 1, M was 2. So that gives us cube root again. So that's what we just derived there from our Rice table, and that matches with the formula. So that explains where the formula came from. But again, me personally, I like the Rice method better than trying to plug in all those variables. But you do whatever makes you feel comfortable. So now at this point, we just have to finish plugging into our calculator. And so I get a value of 0.0143 for S. So that's going to be our molar solubility. And so that's how much will dissolve then in a liter. And so why we want to calculate this? So obviously molar solubility is related to KSP, and we can't always compare just values of KSP to KSP since you have different amounts that disassociate with stoichiometry. So molar solubility then is how you compare different substances. Questions so far? Let's do another practice. So see if you can do the same thing with now silver chloride. So find the molar solubility of silver chloride. And the KSP is 1.77 times 10 to the negative 10. So feel free to use the formula method or the Rice table method, and then we'll go over your answers. did we get answers for S, for molar solubility? So, here, walk me through though before you give me the answer. So did you do the Rice method or did you? All right, so let's do Rice method. And then, so you ended up with something, so plus S, and they were all 1-to-1 ratio. So then we ended up having KSP is equal to silver times our chloride concentration. And then I guess you got KSP equals S squared.
Yep.
Perfect. So what did you get for S then?
I got 1.77 times 10 to the negative 20.
Double check your calculator.
Not 20.
So 1.77. Oops. So you could take this to the power of 0.5. That's one thing, or second square root 1.77. So either way, I type those in. I get 1.33 times 10 to the negative fifth. Is that what other people got?
Yeah.
You got that on your calculator now? Perfect. Yes?
The S in parentheses under silver chloride, is that to show that it's a solid? Or is
Yes.
that- Okay. So
Yeah.
it doesn't have anything to do with the S for solubility?
Yeah.
Okay.
It's just kind of, this is how much solid we're going to put in, since, yeah. And then it's not part of that KSP expression since it's a lump of solid. I forgot what else I was going to say. Oh, yeah, on that note, because I was just thinking, again, always show your work, always, because you never know when little errors like this will occur, but that reminds me of your quiz redo for your pre-quiz, so don't forget about those. I would probably like them by this week sometime, so if you have those today, you can put them up front, but it's always the little things that get people, so always show your work so I can give you credit. All right. And so now we'll look at the effect of the common ion on solubility. And so this kind of relates back to Le Chatelier's principle as well. And so the addition of a soluble salt that contains one of the ions of the insoluble salt decreases the solubility of the insoluble salt. And so let's think about that in terms of Le Chatelier's principle. So if we're looking at this lead chloride dissociation, and so it's shown here. And so what happens when we add sodium chloride? Are we adding reactants or products? Well, so look again. So we're, yeah, your product, right? So your product here is considered chloride from your dissociation. So exactly. So now we add sodium chloride. So it has a common ion effect. And so if we add product, which way does the equilibrium shift? So it goes back towards the left, or favors our reactants. And so if it's favoring our reactants here, obviously that makes it more insoluble now. And so now we can see how to quantify that. So back to reactants. Or shift left. And so now we can do an ICE table again to quantify this. And so now you might want to know, well, what's your molar solubility of calcium fluoride now in your solution that contains 0.1 molarity of sodium fluoride? So let's first grab our KSP. So 1.46 times 10 to the negative 10. And so just like before, we can set up our rice table. So our dissociation of calcium fluoride. And of course, we have our subscript of 2, so we know we make 2 equivalents of fluoride. So then we can set up our initial conditions. And so initially we just have 0. And then it says, well, we have 0.1 molar, so I'll put that for our initial conditions. And then our change, similar to our reaction, so I'll just have this kind of as a side. So if you have this for your solid amount of S, that means you make S, and then how much do you make on the fluoride? Perfect, so 2S. And so now we have our equilibrium values like before. So now S and 2S plus 0.1. And so hopefully this reminds you of all the fun math we've been doing. And so now we can set up our KSP expression. And so that's equal to, we said, the calcium times our molarity of fluoride squared. And so now we can plug it in. So 1.46 times 10 to the negative 10 is equal to S times 0.1 plus 2S squared. And so do we think we can make some assumptions like we have in the past? What do we think? We have this 10 to the negative 10, so that's pretty small. We want to make the math easy on ourselves. Let's make assumptions. Hey, we can always make an assumption and go back if it turns out to be too large. But this is our good clue that we can assume that S is much smaller than 0.1. And so that gives us a little bit easier math then. So then we have S times 0.1 squared is equal to our KSP. And so now I'm just going to plug this in. And so I get this value for S, 1.46 times 10 to the negative 8, which is pretty small. So if we wanted to check that with our assumption, so compare it to that 0.1, since that's what we were looking at. And obviously this is going to be pretty tiny, so that's right 1.46 times 10 to the negative 5%. So assumption was good, and then we have our molar solubility. And I'll just put an aside here that we double check that yes, our assumption was good. You should basically get a better answer or a slightly more refined answer.
I was like off by a magnitude.
math error or?
Yeah, and which accounts for the being off by 92.
Okay. Yeah, so you can always plug this into a fancy calculator too. I was going to try to plug it into Wolfram Alpha, but I was slow. I can double check it later on Wolfram Alpha or something. But yeah, if you don't make the assumption, you should just be able to go through with the quadratic and everything. But the assumption obviously just makes it easier. Other questions on this problem? And so now we can look at the effect of pH on solubility. And so for insoluble ionic hydroxides, the higher the pH, the lower the solubility of ionic hydroxides. And so let's just break that down. And so of course, if we have a higher pH, that means that we have more hydroxide in solution. So that's just the definition of pH. pH increases, so higher concentration of hydroxide. And so that means that for these insoluble ionic hydroxides, if we're looking at the general dissociation, so some metal hydroxide makes whatever metal plus however many equivalents of hydroxide, so probably either 2 or 3. Then obviously if we have more hydroxide at our higher pHs, that causes it to shift back to the left, so towards our reactants and away from hydroxide. And so for insoluble ionic compounds that contain anions of weak acids, the lower the pH, the higher the solubility. So now looking at this metal carbonate species and then the dissociation of that metal carbonate, then we see that carbonate, so the lower the pH, the higher the solubility, and all that's from is since that carbonate then can react with our protonated water, so our acid here, and then it creates this carbonic acid, so that makes it more soluble in solution. This is also probably interesting environmental chemistry. So you could talk about, this could be a good Earth Day topic for a project, so looking at carbonate and how all that is influenced with the solubility and pH. So it could be interesting. All right, so take a minute or so and determine whether each of these compounds is more soluble in an acidic solution than in a neutral solution. So while y'all are thinking about that, I just wanted to show the Wolfram Alpha solution to that previous problem. So if you were unsure or wanted to double check yourself, so Wolfram Alpha, I don't know if y'all are familiar with it, but it's just a computer that computes things, and it's pretty useful. And so you can just watch how you type stuff in, so it does accept like the E thing, and it just make sure it reads everything correctly in this like input interpretation. So I just plugged everything in without the assumption though, and then blah, 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 and it still came up with our same answer of about 1.46 times 10 to the negative 8. So that's just another tool to help check yourself with. Just wanted to make sure everyone was satisfied. Do we need a few more minutes on this one, or?
So we go over one of these and then maybe like take another minute? This doesn't really make sense to me, and so I don't know kind of where to start.
Can I ask you?
Yeah. Let's walk through, because, well, barium fluoride is a tricky one, but let's walk through it together. And so one thing that I would do is kind of analyze our ions. So barium, is that neutral or acidic when we think about the salts? So neutral, so we don't really have to worry about barium. But then what do we remember about fluoride? So it makes HF. And well, let's draw that reaction of making HF. So fluoride, and so it can react with water to either form HF plus hydroxide, or if it's reacting fluoride plus an acid solution, gives us HF plus water. And so what does this make fluoride? Acidic, basic, neutral? So basic. And so now we do have to worry about it. But you said it makes HF in solution. And so now looking at this, and let's think about our dissociation reaction. So we're making barium plus 2 equivalents of fluoride. But then we said, well, it can go on to react in probably this manner is the one we want to look at because we're comparing acidic versus neutral solutions. And so what do you think, how will this affect the solubility then if the solution is more acidic? So think back to Le Chatelier's principle too. Yeah.
Since you're taking fluoride ions out of solution, it would, the equilibrium might want to go more to the right.
Exactly. And so does everyone see that? So, right, we consumed our fluoride into this reaction. So as it's more acidic, right, it forms HF. And so, yes, we're using our fluoride. It's being consumed. And so this drives the barium fluoride more to the right. And so then we can say that we expect it to be more soluble in acidic conditions. So does that kind of make sense how to analyze these questions as well? So you're kind of seeing, you know, do my products, can they react with acid then and be consumed? So now take another minute or so for silver iodide and calcium hydroxide and see if you think they're more soluble in acidic or neutral solution. So walk me through silver iodide and what we thought. Where went my pen? So what do we think about silver iodide? Yeah, and we can also say, right, that they're neutral too. And iodide is also neutral. So would it have any effect to be in an acidic solution? So I see some no, so probably no effect. And then what about calcium hydroxide? So what do we think about calcium hydroxide? Yeah.
The H would be consumed by the hydronium in an acidic solution, leading the reaction farther to the right.
Yep, so that is good. So hydroxide reacts, we want to say, so more soluble in acidic conditions. And so I like the idea of writing out the reaction somewhat, just so we can show that our product in our solubilization reaction gets consumed by our acid. And so that's a good way to see Le Chatelier's principle. Yeah.
So for the silver iodide, it would be more soluble in a neutral solution because they're both neutral?
Yeah, or just like no effect with acidic, so pH probably wouldn't change its solubility. Any questions on these? All right, we are marching through the chapter, but that's good. Trying to get ahead of lecture here. And so now we can go through precipitation and kind of this selective precipitation. And so now we can say, well, we know that precipitation will occur when the concentration of the ions exceed the solubility of the ionic compound. So we calculated that for molar solubility. And then so we can know when precipitation will occur. And so now these terms, and this is why I always feel like second quarter and third quarter are kind of a blur of equilibrium constants, because now good old Q is back. And so just like before, right, Q just gives us our snapshot. So then we're seeing, you know, are we greater than our KSP? And so, right, if we had Q greater than KSP, and just think back, what was my KSP? So whatever ion, right, to whatever times our anion. Of course, now I need more variables. And so basically, if we're saying our snapshot is above or greater than our KSP, then we know that our solution is oversaturated and that we will get a precipitate. And then just like before, so if we take our snapshot of Q, and then if it's less than our KSP, then we know it's unsaturated and we will not have precipitation. And then if we take our snapshot of Q and it's equal to KSP, then our solution is right at saturation, and so no precipitation will occur. But of course, right, you add one more spec and then you will have precipitation. And obviously Q is the same formula as KSP, right, just our snapshot. So I'm trying to emphasize that. So we use the same formula, we're just taking it at a certain snapshot, and so we're trying to figure out whether it's obviously forming a precipitate, not forming a precipitate, or right at that line. And so some solutions with a Q greater than KSP will not precipitate unless disturbed. So this is when you have a supersaturated solution, usually made when you like boil something really hot, and then add a bunch of your solute, get it really concentrated, and then sometimes it won't crystallize unless you disturb it, so you can like scratch it, and then that would cause for a point of nucleation, and so that's when you get pretty crystals. Sometimes you can also pour out these solutions, and then they just kind of crystallize as you pour them out. So that's always fun. And so again, just little depictions here. So precipitation occurs if our Q is greater than KSP. And then we can also use what's called a seed crystal. So if you have a supersaturated solution, and this works well with sodium acetate. I'm not sure why, in particular, sodium acetate is good at this, but you can either put a seed crystal in and it will start to crystallize, or sodium acetate is one where if you kind of pour it out, then it'll start crystallizing all over the place and on your jar. All right, so now we're going to go through and how to figure out this scenario. So now we have a solution containing lead nitrate is mixed with one solution containing sodium bromide to form a solution that is 0.015 molarity in lead nitrate and 0.0035 molarity in sodium bromide. So does a precipitate form in the newly mixed solution? So let's go through how we're going to analyze this. And so, of course, the first question is, well, what is our precipitate? So we have these two solutions, so lead nitrate, sodium bromide. And this is kind of thinking back to our other chapter. So first quarter chemistry. These ions are floating around. So what's going to be the insoluble product? What are the possible new combinations? What's the insoluble one? And if people need new solubility rules, charts, I can also print some out for Thursday. But there's only two possibilities of new products, and then from there, it should be obvious which one is the insoluble one.
So would it be lead, bromide,
Exactly.
and sodium nitrate?
Yes, except so sodium nitrate, right, that's the soluble one, so we don't care about that one as much. But then, and we could go back to solubility rules, but if we remember, right, sodium's usually soluble, nitrates are usually soluble. And so exactly, that leaves us with our lead bromide. And so this is going to be our insoluble compound. And so now we can at least start putting some numbers to this and also doing kind of our rice table and going through our analysis. So now that we know what the insoluble portion is, we can write out our reaction. And so that's just lead bromide. And of course it's going to disassociate, make lead, and drop my 2 there. So something like that. And let's get our KSP. Let's see, is lead bromide under here? Lead bromide, so 4.67 times 10 to the negative 6. And so now let's write our expressions, and then we'll plug in some numbers. And so just kind of S, S2S, and we could also say, we could also plug in numbers. This probably wasn't necessary. So we need to say, well, if Q is greater than KSP, then we have a precipitate. And so that means we need to plug in our snapshot. Yep, kind of ignore that, sorry. And so what's our concentration then of lead just initially? So from this mixture. Of lead, because it's 0.0035 in sodium bromide. Yeah, so then it's 0.015 in lead. And so let's write our KSP expression. So it's going to be lead times our concentration of bromide, right, squared. So now we're plugging in our values. And so now this is our Q snapshot. And so it's 0.015 in lead. And then that means it would be 0.0035 in bromide. And of course it's squared. So we can plug that in. And so now we're trying to see if Q is greater than or less than our KSP. So let's plug that in. So 0.015 times 0.0035 squared. And so I get a Q, our snapshot, of 1.84 times 10 to the negative 7. And so now let's compare this number to, well, we set the KSP as 4.67 times 10 to the negative 6. And so does that mean a precipitate will form in this newly mixed solution? So no, exactly. So it's no, and we can say it's no. So we'll say no precipitate, since our Q is less than our KSP. So questions about this one? So now let's see how we might use solubility techniques to separate out mixtures. So we say a solution that contains several different cations can be separated by adding a reagent that forms an insoluble salt with one of the ions but not the others. And a successful reagent can precipitate with more than one of the cations as long as their KSP values are different. And so let's see how this would work. And so this is a good purification technique. So magnesium and calcium ions are present in seawater. And so there it gives you the different molarity amounts. And they can be separated by selective precipitation with potassium hydroxide. And so what minimum hydroxide concentration triggers the precipitation of the magnesium 2+ ion? So let everyone stare at this for a minute or so. Think of how you might set it up, and then we'll go over it together. All right, so what values do we need to maybe solve this? And then did we at least start setting up how we can calculate this potentially?
So you need a KSP greater than magnesium hydroxide, right?
Yeah, or right at that. So we could just use the KSP. So what's the KSP of magnesium hydroxide? Do we have that?
5.6 times 10 to the negative 12.
So 5.6 times 10 to the negative 12 for the KSP of magnesium hydroxide, correct? All right. I have a different number, but I also have this number, 2.06 times 10 to the negative 13. That's funny. I'll just go with this value then. So 5.6 times 10 to the negative 12 for magnesium hydroxide. All right, so then how do we set up our problem? So what can we do after this? We're at least given magnesium concentration. And then you were saying something, what were you saying about?
So the KSP has to, I don't know.
So let's write out our reaction then. So then we have, reaction, magnesium hydroxide, disassociates to make magnesium, plus 2 equivalents of hydroxide. And then let's write our KSP expression. So you have the right idea. We need to figure out, well, what is our hydroxide concentration right at this limit? And so our KSP expression is just our concentration of magnesium times concentration of hydroxide squared. And then, well, we're given the initial conditions of magnesium, so how many ions we have in solution in seawater. So we can plug that in for our magnesium concentration, and then we just have to solve for hydroxide. And so let's plug in these numbers. So 5.6 times 10 to the negative 12 is equal to 0.059 times s squared, or x squared, whatever variable we want to use. So in this case, since we just need x, I'm just finding concentration. So yeah, I'm not trying to find molar solubility, or else you would be correct. So right now I'm just trying to find how many ions, not based off of anything. Oops. So I get x of like 9.74 times 10 to the negative 4. So I see other people got that. 10 to the negative 6, sorry, for our molarity. And so again, that's just minimum concentration of hydroxide then. So now let's ask a different question with this problem. And so now we'd want to know, so part B to this, at what concentration of hydroxide ions will calcium hydroxide precipitate out? So now we're comparing kind of our magnesium versus calcium hydroxide solubility. So see if you can do this one. We went through one of them together. So I'll give y'all a minute or so. Just try to set up the second part. ions, and then that should say will calcium hydroxide. It looks like I wrote with though for some reason. How's our part B going? Let's see, were we given, so we're given, so this time we want to use the calcium hydroxide KSP. And so this value has 4.68 times 10 to the negative 6. If your book says something different, that's fine. So on an exam, I'll probably give you the KSP, but I expect there to be discrepancies. So KSP, 4.68 times 10 to the negative 6. And then how can we set up our KSP expression? What is it, or? Yeah. So then it'd be equal to the calcium concentration times what? Times hydroxide. And then don't forget squared, since there's two of them. And you can always write out your reaction. So I'll write out our reaction so we can remember how many we have of each one. And so now that we have this expression, and then we're given how much calcium there is in the C, we just have to solve again for hydroxide. So 4.68 times 10 to the negative 6 is equal to 0.011 times x squared. And so what do you get when you solve for x?
I got 0.0206.
0.02? I don't know why I have a different. Perfect, so 0.0206 then. Excellent. And so that's going to be molarity. And so that's the concentration of hydroxide ions that makes calcium hydroxide precipitate out. Excellent. Did everybody get this? Perfect. And so let's ask one last question to this. And so now this is good. We can see the difference in molarity that precipitates out these different solutions. But to truly assess whether it's an effective separation, we have to ask, so what will be the concentration of magnesium 2+ ions when the calcium hydroxide is precipitating out? So see if you can figure out, well, what would I even be plugging in to my expression? What would I be solving for? And we'll go over it.
But if you had, assuming that these numbers that we just got are correct, when we did the magnesium, it said that we needed a minimum of 9.74 times 10 to the negative 6 molarity of hydroxide.
Yes.
So like if the molarity of the hydroxide is high enough to make calcium precipitate out, wouldn't it also make the magnesium precipitate out?
Exactly. So, I mean, that's part of what, or, sorry, the other way.
Or am I, sorry, am I solving the question out loud and not realize? Does my question make sense?
Yes, sorry, I'm just like trying to answer it better. So, yeah, you might be answering the question. So we're seeing, right, this has a pretty low KSP. So then this would trigger this to come out of solution, right? And then you also have this question. So this KSP is slightly, right, more soluble. So then this triggers it to precipitate out. But then we're kind of asking the selective precipitation. And so once we get to this final question, we're asking, like, you know, is there magnesium basically still there when your calcium is precipitating out? No, it's a good question. So then what did you need to plug into this concentration to ask this question? So we have all the pieces. So essentially we're saying, like, imagine you're titrating in hydroxide in. And so, right, you added this amount. your magnesium hydroxide started precipitating out. Now you got to this amount of hydroxide, so your calcium hydroxide is starting to precipitate out. But then you're asking, well, is there still magnesium 2 plus when your calcium hydroxide is precipitating out? And that, I think, really is what your question is how is this effective, essentially? And, well, let's answer that. And so all we need to do is we can refer back to this expression, right? So going back to our KSP of magnesium hydroxide, except we want to solve for our magnesium concentration, and we know the hydroxide because we said, well, what's the concentration of magnesium when your calcium is precipitating out? So we said, well, this is what it takes for the hydroxide concentration for calcium to precipitate out. So now we can plug this in for hydroxide. So let's write that down. So we have our KSP for magnesium hydroxide, and so I have to look at the number again. So we said that was 5.6 times 10 to the negative 12 is equal to magnesium concentration times hydroxide squared. And so we want to know, well, by the time we're precipitating out our calcium, how much magnesium is left in solution? And so let's plug in our hydroxide concentration from before, so 0.0206 squared. Now we're solving for magnesium is equal to this KSP. And so I get this for my concentration of magnesium. So is this what other people get? So I see some nods. And so now all that we're saying is, well, once your calcium hydroxide is starting to precipitate out, then you still have 4.67 times 10 to the, sorry, I pulled out from my old notes. You still have 1.32 times 10 to the negative 8 concentration of magnesium. But, you know, that's pretty small molarity, that negative 8. And especially, right, go back and what we started with. So we started with 0.059 molarity just in our seawater. Then we started doing the separation, and now we're saying once my calcium hydroxide is precipitating out, that means we took out most of the magnesium ions from solution, but there's still 1.32 times 10 to the negative 8 molarity left. But for our purposes, this would be considered an effective separation. So that is a pretty small amount, so that's considered effective separation. So did that answer your question, essentially? So it's kind of answering, like, was this process effective? And, you know, if they had been closer in solubility, then it probably wouldn't be as effective. And then you could calculate that and say, well, you know, there's actually a high enough concentration of magnesium still, or whatever ion, and maybe that's not an effective separation technique.
So I could read that in the opposite way, where we like looked at calcium instead of magnesium, there would have been a bunch of calcium left over, right?
Yeah, like if we're trying to separate.
Sorry for all the questions.
No, they were good questions, and sorry I went over time. And then today is a good day to go over calculations. So if you want to go over calculations from last week, just hang around after class. Otherwise, I will see y'all on Thursday.